Things in this chapter, and as we go, are going to increase in difficulty a little bit. We are stepping it up as we go through the semester. And what you'll find in the majority of these chapters is that we'll start out with characteristics. So what is this system that we're looking at, and what does it do? After that, we look at anatomy. Okay, so what is the structure of a muscle? So we're going to go next. And then finally, we move to the physiology of the chapter. Okay, and the physiology for muscles is contraction and relaxation. Okay, so that's where we are heading. We are going to get through 1 and 2 today, and we are going to start on 3. Y'all ready? Yes. Okay, functions of a muscle. So, muscles help you move. That's the first one. Okay. Secondly is posture. So it helps your body withstand the effects of gravity. Okay, you guys have experienced this. Well, maybe you haven't. Maybe it's just me who is lazy and doesn't exercise very much. Okay. Okay, so you decide you're going to exercise, and you do some ab muscle exercises, right? And you work on them, and then like the next day they're really sore, right? And then every move you make, you feel those ab muscles. You guys have those experiences? And so you decide, that hurts too much, I'm not going to do it again tomorrow. And then you go another month or 2, and then you decide to do it again. But your core muscles, so the muscles around this area, the muscles around your vertebral column, they are working on posture, on holding you up straight, on making sure you don't wiggle, woggle, and fall down. Okay? And you feel that when you work those muscles out. You feel it the next day, every move you make. Okay? So that's posture. The next one, joint stability. We talked about this a little bit when we talked about joints, when we looked at that knee with the quadricep muscle attached. So keeping the joint stable and preventing it from coming out of alignment is partially due to those muscles that are strong around them. Okay? And then finally, we have heat production as a function. And we'll talk more about that when we get into cell respiration and metabolism and all that stuff. Okay, but your muscles use a lot of energy, and a byproduct of using that energy is heat. All right, characteristics of muscles. All muscle tissue exhibits excitability, which is also known as irritability. Guys, your muscles are excited. Isn't that good? Yeah. Okay, now, in anatomy, we always say that muscles are excitable. It means that they can respond to a nervous impulse. Okay, it can respond to the nervous system. It can be excited by a neuron. Okay, we have contractility. What does that mean? It can contract, which means it can get smaller, right? And we have extensibility, which means that it can stretch. It can get longer. Okay, but we also have elasticity. That means whichever one we do, we can always go back to rest, the resting one. Okay, so contractibility gets smaller than normal, extensibility gets longer than normal, but elasticity we can always return back to normal. Okay? All right, so all muscle tissue has those characteristics. Okay, you have learned in our study of tissues that there are 3 types of muscle tissue: skeletal, cardiac, and smooth. Which one of those have striations? Skeletal and cardiac. Which one of those is voluntary? Skeletal. So, in this chapter, we are focusing on skeletal muscle. Okay, but don't panic. We will talk about cardiac muscle when we get to the cardiovascular system next semester. And we'll hit little bits of smooth muscle when we talk about the organ systems that contain smooth muscle. Okay? But right now, we are focusing on skeletal muscle, which leads to this first bullet, what you just told me. Skeletal muscle is voluntary, and it's striated, and it's usually attached to a bone. Talking about those levers, it pulls on the lever to help move it. All right. Striations, you can see them in the picture in the back. These are our bands, our light and dark bands. Guys, today you are going to learn what makes light and dark bands. Are you excited? I know you've been waiting a long time for this. Okay. This second bullet, I'm going to read it and then I'm going to tell you what it really says. Okay. It says during muscle contraction, the muscle generates internal tension followed by external tension that moves the load. So during muscle contraction, something that happens inside the cell on a small scale causes a big change. Okay? So we're going to look at that small scale change that will cause the contraction of the whole muscle on the outside. Okay? All right. Now, some anatomy. You guys know this picture, right? This might have been on your practical. Was it? No, but it could have been. Could have been on your practical. Okay, so we have these beautiful bands that we'll get to in a second. The nuclei are all shoved to the side. And we have a muscle cell, which is called a muscle fiber. Okay? You will learn as we go through this section that we like to name things weird things when we're talking about muscles. We take everything that we knew that was normal and give it a new name. All right. So, anatomy. We are going to start with a big, complete muscle, and then we're going to zoom in little by little. Okay? This is a diagram you need to know for your test. It's one of your objectives. So, let's start. A muscle is surrounded by a layer of connective tissue. Okay? So if you cut open your arm and you looked at your biceps, you're not going to see the muscle tissue. You're going to see the connective tissue that surrounds that muscle. Okay? The connective tissue on the very outside is called either epimysium or epimysium. Okay? I usually say epimysium, but either one is fine. Okay? Sometimes I use both. Sometimes I just throw them both around in the same sentence. Okay? So, epimysium on the outside. Now, within this big muscle, there are smaller bundles of muscle cells. Okay? These bundles are these circles in here. Okay? And they are called fascicles. Okay, so it's labeled right here, but really we can look at this guy right here. That's a fascicle. Okay? A fascicle is also surrounded by connective tissue. This time it's called paramecium. Okay, so epi on the outside, peri in the middle, and then inside of this fascicle, we see the individual muscle cells. And those individual muscle cells are called muscle fibers. And the muscle fibers also have connective tissue wrapped around them. And that connective tissue is called endomysium. So epi on the outside of the muscle, peri around the fascicle, and endo around a muscle fiber itself. Okay? You'll also see blood vessels are labeled here. So throughout our muscle itself, there's lots of blood vessels, the arteries and veins traveling through it. And we have a tendon labeled. So a tendon is used to connect the muscle to bone. You also see muscles connected with bones in a flattened sheet, a flattened tendon called an aponeurosis, but you'll see that later when you look at specific muscles. Okay? All right, so let's see what you remember. Muscle is surrounded by, okay, inside of a muscle are smaller bundles called fascicles. They're surrounded by, inside the fascicles are, and they're surrounded by. Perfect. Okay, you all ready to zoom in some more? Okay. Now, we're zooming into the muscle fiber, so the muscle cell. So a lot of these parts are parts you already know, but we're going to give them different names because we can. Okay, here we go. The plasma membrane of a muscle fiber is called the sarcolemma. It's still the plasma membrane. It's still on the outside of the cell. He just has a fancy name. And he's the sarcolemma. Now, something special about the sarcolemma. He has what are called transverse tubules, or T tubules. So, if I draw a picture over here, we have a normal looking cell. right? These T-tubules are little tubes, little tunnels, that are going to come off of the main plasma membrane and go into the cell. So, for instance, we may have a little tunnel that starts right here and spreads out and goes back to the surface over here, goes back to the surface over here. Okay, but then these may branch off too. Okay, and we just have this branching network of the plasma membrane inside of the cell. So it's like the plasma membrane tunnels into the muscle fiber. Now, this is important because muscle contraction is going to start by changing the resting membrane potential. Okay? So remember, our resting membrane potential has what charge inside, what charge outside? Positive outside, negative inside. In order to start a muscle contraction, we have to flip those. We have to get it to be positive inside, negative outside. And we have to send that signal all the way to the inside of the cell. Okay? So if that's starting on the surface, and this membrane's starting to flip, we also need that to go into the cell. So we have these little tunnels, these little passageways for that signal to travel on to get inside. But it's all still connected to the plasma membrane. It still has the same properties of the plasma membrane. We're just getting a way to get that signal deeper into the cell. Okay? Yeah. No, it sits on the outside though. So the sarcolemma is the plasma membrane. Okay? And then the endomysium is a connective tissue layer that sits on the top of it. Yeah.
They're used for changing the resting membrane potential, or like transmitting signal?
They transfer the signal of that resting membrane to go throughout the cell. So they are the plasma membrane. They are the plasma membrane, just extending that plasma membrane into the cell. So we're carrying it on deeper. It's all connected to the surface. Great. Any other questions? Okay, our next cell part that we're going to get to is the cytoplasm. You guys remember what the cytoplasm is, right? But now, because it's a muscle fiber, we're going to call it the sarcoplasm. Yeah, okay. So if you see the prefix sarco, you should automatically think muscle. Okay, inside the sarcoplasm, you're going to see lots of myofibrils made up of myofilaments. Okay, that's what these packages are. So the packages are the myofibrils, and inside the myofibrils are our filaments that we're going to get to on the next slide. Okay. We also have a lot of glycogen and myoglobin. Anybody remember what glycogen is? You have to say it louder. I hear some people saying it. Sugar. Sugar. Glycogen is sugar. There's stored sugar in that cell. So, he's a muscle. He needs lots of energy. So you have lots of sugar stored there in the muscle so that you can use it to contract. Okay, our next cell part is the endoplasmic reticulum. So because we're a muscle cell, we are now the sarcoplasmic reticulum. Right? Okay, and the sarcoplasmic reticulum is a modified smooth ER, and his job is to store calcium. So he's a calcium reservoir. Okay, so he stores up the calcium until the cell needs it. He'll release it all quickly, goes out into the sarcoplasm, and then when it's done, it'll be stored back there in the sarcoplasmic reticulum. Okay, so sarcoplasmic reticulum stores calcium. Now, a little bit of structure here. On our picture, these gray stripes are the T-tubules. So they're the tunnels coming in from the sarcoplasm, or sorry, the sarcolemma. See, I get it mixed up too, because they're just such weird words. Okay, so they're the T-tubules coming in. Around either side of them are these blue meshy things. That's your sarcoplasmic reticulum. It's the blues of the sarcoplasmic reticulum. At the edge of the sarcoplasmic reticulum, where it meets the white T-tubule, you'll see these enlargements. Okay? So you go from having a nice spread out mesh to a bigger area of blue. So this area right here, this area right here, okay, is an enlargement. That's your terminal cisternae. So think of a cistern, a big gathering area. Okay, so that's gathering at the end of the sarcoplasmic reticulum. That happens right beside the T-tubules. So there's a terminal cisternae there, 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 and there. Okay, so it's right beside the T-tubules. Now, finally, we call this collection of a T-tubule with two sarcoplasmic reticulum terminal cisternae on either side a triad. So that's the triad right there. It has three things in it. It has a T-tubule in the middle and terminal cisternae on either side. Okay? Now, we will come back to I bands and A bands and Z discs and H lung and M line in a second. Okay, don't worry about those yet. Yeah.
Each side is considered like a bunch of players, so it's not just since they're all the same name, they're going to consider it.
Right, because there's two of them. There's one over here. Yeah. That's why it ends up being three. The triad. All right. Any other questions? Okay. So it's important that we know our parts before we figure out how it's working. Okay. So if you do have questions, make sure you ask. All right. So moving on, we get to zoom in even farther. So remember back on this slide, the slide before, oops, a little bit farther. We have these big groups of myofibrils, and we said inside the myofibrils are myofilaments. That's what we're looking at now, are those smaller myofilaments. Okay? There are two different types of myofilaments. There are thick filaments and thin filaments. The thick filaments are called myosin, or they're made of myosin, and they're shaped like a golf club. So they have a long part, a long tail, and then there are two heads at the end. Okay? Right, so that's myosin. And the heads can rotate. They can move. Okay. Then we have thick filaments. We also have thin filaments. Okay? The thin filaments are made of actin. They look a bit different. They're these little beads, the actin subunits, that get formed together into these ribbons that wrap around each other. Okay? So the blue in the picture is actin. Now, I have problems remembering things, as you know. So it's hard for me to remember which one's thin and which one's thick, actin versus myosin. The way I came up with is that actin sounds kind of like you're active, and if you're active, you may be more of a thin filament, and then myosin is not active, so they're not active, so maybe they're a thick filament. I don't know, it kind of works. Okay, so we've got our thin filament made of actin. Now, look at our actin subunits. Do you see anything fun on the structure of the actin subunits? They have myosin binding sites. So the thick filaments are going to bind with the thin filaments. Yeah. Okay. So we got those. Now, we also have two other proteins here involved in the thin filaments. We have tropomyosin. Tropomyosin is this orange string that lies along the actin subunits. Now, can you tell me what has been covered up by the tropomyosin on the actin? Those myosin binding sites. Okay, so as long as that tropomyosin is in place, the myosin binding sites are covered. Okay, see our pictures all coming together now? We're building a story. Okay, our other guy here is troponin. He's this yellow guy. troponin holds onto the tropomyosin, and he can move it. So the troponin can move the tropomyosin out of the way and expose those myosin binding sites. Yeah. Fun? Okay, so we got actin with our troponin and tropomyosin. Okay, questions? Yeah.
So is there like a reason that it's initially, like the sites are initially being covered?
Yes. Yes. Okay. Yeah. So we want them covered now so the myosin can't bind. But then when we're ready to contract, we'll move it out of the way and let the myosin grab hold of it. Yep. Okay, any other questions? This is all foreshadowing to where we're going. Great. Okay, so here's what we've got so far. We've got a muscle that's surrounded by epimysium. Inside the muscle is a fascicle surrounded by paramysium. Inside the fascicle is a surrounded by endomysium. Then if we zoom in, we will see our muscle fiber surrounded by, what is a plasma membrane called? Sarcolemma. Okay. Inside of there, we have our myofibrils, which are collections of these myofilaments, the thick and thin filaments that we just saw. Okay. So it all comes in here. Let me push this next button. You can see that this orange is the myosin that we saw on the last slide. And the blue is the actin. Okay, now's where I want to tell you about the bands and the zones. Okay, this is where all of your questions about the striations and what makes them dark and light, they're all going to be answered. Okay, so if we look at our muscle fiber, we see up here there's dark and light bands. Okay, we're seeing dark bands, we're seeing light bands. We're still seeing dark and light bands in here. The dark bands are the A bands. The light bands are I bands. Okay, what makes them light and dark? Here we go. If something is thicker, it's going to be darker under the microscope. Okay? If it's thinner, it's going to be lighter. So, the I bands, the light zones, are right here, which lines up with this right here in the bottom picture. The only filament that we have in that light band is actin. Okay? So the I bands are only actin. Okay? Now, the way these actins and myosins are arranged are overlapping each other. Okay? But they're not completely overlapping. They're kind of staggered. This gives room for the myosin to grab the actin and to shrink it and cause contraction. Okay? But at rest, they're staggered a little bit. So that's going to give us an area that's only actin. Then an A band, the dark band, is anywhere that myosin is present. Okay? Now, this does not mean that there's only myosin there. Okay? But the dark band is anywhere you have that thick fiber. Okay? That includes areas where actin and myosin are on top of each other. It also includes areas that are only myosin. So what we're going to get is inside of that dark A band, a smaller zone called the H zone. It's right up there. Okay, so inside the A band is an H zone. This is the area where there's only myosin. Okay. is actin and myosin, and then the H zone only myosin. But the H zone lives within that A band. Okay, it's included within it. Okay, then there's only two things left. There's two lines. Okay, the M line is in the very middle of the H zone. Okay, so the M line are where the myosin tails connect to each other. Okay? And then that means that our last one is a Z disc, which is in the middle of an I band, and that's where the actin tails connect to each other. Okay? Now, I realize this is complicated. Now, I realize there's a lot of letters being thrown around, doing lots of different things. Okay? But I encourage you to look at this bottom picture. Okay? So, A band is anywhere myosin is. I band is anywhere that myosin is not, or anywhere where we only have actin. Then we have a region here in the middle. That's the H zone, where there's no actin. It's only myosin. And he sits within that darker A band. So he's part of the A band. And in the very middle of that H zone is the M line where those myosins connect to each other. And then in the I band, the light band, the Z disc is where the actins connect to each other. Okay? And that's why we see dark areas and light areas. So on our striations here, the light areas are where there's only actin. The dark areas are anywhere that myosin is present. Yes?
Why is the M line called the M line?
I don't know. I don't know why they decide to name things the way they name them. You can look and see if you can figure out why one's a line and why it's a disc. It may have to do with the arrangement of the proteins that are there that are holding it together. You need to look and see if you can find out. But I don't know what the correct answer is. All right. Any other questions? Yeah.
So how is there actin in the A band too? Because the I band is light, so it's actin, but the A band is dark.
It's where they overlap. Okay, so if this one is myosin and this is actin, they sit like this when they're at rest. So the light band is right here where there's only the light band, or the actin. And then from here over is going to be a dark band because myosin is there and myosin is thick, so it makes it turn dark. So it includes this area where they overlap each other. Anything else? Okay. So this may be one that you have to sit and look at the figure for a little bit to kind of make it sink into your head. But I have no doubt that you'll be able to do it. And if you have questions, you're always welcome to ask. All right. Now, let's see this next. So, this top picture is what we just looked at. Muscle fibers at rest. So there's a little bit of overlap. We've got our myosin, we've got our actin, they're sitting close to each other. To have a muscle contraction, the myosin heads are going to grab onto the actin and slide it together. That will make the overall length of the muscle shorter. So as you start out, they're overlapped, but not completely. And then at the end of contraction, we end up with the myosin and actin overlap even more. Okay, so we've slid and made it shorter. What this ends up doing is it makes those I bands, the area where there was only actin, shrink. Because the myosin and the actin are being pulled closer together. So there's less area where there's only actin. Okay? Because the actin and myosin are overlapping more and more and more. So let me start this video again. See if we can do it there. Okay, to see what's going on. So, these are the myosins moving, the reds are moving. At rest, they're far apart. We've got a big, oh sorry, that's the actin is red. When they're at rest, we have a big I band, but as they get pulled closer together, our I band decreases. Our A band stays the same though, because the myosin doesn't change size, it just pulls the actin closer together. Okay? So during contraction, the muscle fibers shorten. The thin and thick filaments slide past each other, causing the whole cell to shrink in length. We are going to get more of this, okay? So if this doesn't make sense yet, we're going to build it up. We're going to build our story, okay? All right. You may want to think of it, people rowing a boat, or oars, or like the myosin heads that pull along a little closer. I don't know. Okay. Now, contraction and relaxation of skeletal muscle fibers. We are now getting into the physiology. How does this process happen? Okay, we've covered the anatomy. We've talked about the players. Now we're going to look at how they do their job. This is a fundamental physiological process. Okay? You're going to have to memorize it. You ready? Here we go. Okay. So, taking a big picture approach to what's going on. When a muscle contracts, the first one, or the first instance that you have of this muscle contraction starts in your brain. So it all starts there. And your brain says, hey, I need to move that muscle. And so it sends information through a motor neuron to the spinal cord. Okay? The spinal cord then sends the information along an axon. So an axon is a long portion of a neuron. So it's a long extension. Okay, and here's a picture of an axon coming down to a muscle fiber. At the end of an axon, the axon kind of bulges out into this bell-shaped thing. This is called an axon terminus. So it's the very end of an axon. Then the signal will be passed from that axon terminus to a muscle fiber across what's called the neuromuscular junction. So the neuromuscular junction is just this area right here, where that axon terminus gets really close to the muscle fiber. Now, it's important to note that the axon does not touch the muscle fiber. There's a little space between there. And if you look at the picture, it's labeled right here, the synaptic cleft. So the synaptic cleft is the little space between the axon terminus and the muscle fiber. Okay? So it's all going to start in the brain. You say, I want to contract the muscle. And then it gets sent all the way down, so eventually it gets to that muscle fiber. Okay? Also note, we'll come back to this later, that one axon will split as it gets close to the bottom. And so we're going to activate multiple muscle fibers at the same time. Because remember, a muscle fiber is an individual muscle cell. So we have to have a couple muscle cells working together to actually make a difference. Okay? All right. This process takes place in 3 main steps. And we'll get to that in a second after we review the concept. I forgot this not here, but it's important. Okay. Resting membrane potential. Let's see what you guys remember. Okay? If this is my cell, and he is at rest, what do you know about him? More negative inside, which makes the outside more positive. What is there more of outside? Sodium. What's there more of inside? Potassium. Good. All right, and that's our resting membrane potential. More negative inside, more positive outside. When we want to send a signal, we're going to flip it. We're going to make it more positive inside, more negative outside. We're going to get to that in a second, okay? The next thing I want to talk about is your sodium-potassium pump. What does he do? 3 sodiums for every 2 potassium. Okay, and which direction is it sending the sodium? Okay, we want to put it where he wants to go. So we're sending 3 sodiums out, we're sending 2 potassiums in to help maintain this process here. Okay? Now these next two, I don't remember if we talked about these when we talked about channels, but we're going to talk about them now. Okay? So ligand-gated versus voltage-gated channels. So these are channels that span the membrane. So they're little passageways for things to go through. These channels can be gated, meaning they have a gate on them, and the gate can only be opened at certain times. Okay, once that gate is open, things flow freely through, but then the gate can be closed. Okay? There are 2 ways that we're going to talk about to gate the channel. One is a ligand-gated channel. That means there's going to be a molecule, something that binds to that channel and acts as a key to open it up. Okay, so this channel is closed, but a ligand can come and bind to it, work as a key, and now it's open to allow things to move in and out. Okay, so that's a ligand-gated channel. We also have voltage-gated channels. Voltage-gated channels open when the voltage changes. So if the cell is normally negative inside, positive outside, okay, and there's this channel sitting right here, he's normally closed, but if we change the charge around him and make it positive inside, negative outside, then he will open up and allow things to move. Okay? So instead of something actually binding to him as the key, the voltage change is the key that allows it to open up. Okay? All right. We will talk about action potential as we go. But are there any questions about those 4 things up there? All right, good. Good, good, good. Then, now let's move on to the 3 parts of a muscle contraction. Okay? We're going to start with number 1, getting the signal through that neuromuscular junction. But then we also have muscle fiber excitation, contraction coupling, and then if we get even down to the smallest scale, is that cross-bridge cycle, the myosin moving the actin. Okay? So this is where we're going. But we are going to start with step 1. Okay. All right, deep breath. You ready? Here we go. I heard sigh instead of deep breath. Okay. So we're starting at that neuromuscular junction. What is happening right here between the axon terminus and the muscle fiber? Okay? These are all the steps together, but we're going to go through each of them one by one. Here we go. Step number 1 says an action potential arrives at the axon terminal of the motor neuron. Okay, what does that mean? That means the signal that was sent from your brain to your spinal cord has made it to the end of that axon. Okay? So the signal has reached the axon terminus. Now, that signal is in the form of an action potential. Now, we haven't talked about what an action potential is yet, but an action potential is the movement of this flipping of charges. Okay? So what happens along that axon, okay, moving this way, we start out with everything being negative inside, positive outside. Okay? But a signal is going to be sent through that axon, through a process that we'll get to in the nervous system, it's not important right now, where we flip these charges. Okay? And we keep flipping it all the way down until we get to the very end. So we've just flipped and made the inside positive and the outside negative. How that happens isn't important right now, but we have now a difference in voltage. Okay? So we've gotten a signal down here to the end, and we are now flipping the charge on this plasma membrane. So now we have the inside positive and the outside negative. That's the action potential that's come through. And we flip the charges. Okay? All right, so now we have in this terminal, the axon terminal, we have the inside positive and the outside negative. Now, step number 2. We have voltage-gated calcium channels. Now, those calcium channels were closed, but now the action potential is there, and the action potential says we're now positive on the inside. What's that going to do to the voltage-gated calcium channel? It's going to open up. Okay? So the voltage-gated calcium channels now open up because they had that change in voltage come down from the axon. Okay? He's open, which allows the calcium to come inside the axon terminus. Okay? Originally, there wasn't much calcium there, but we've opened up the channel and we've allowed calcium to come in. Okay? So now we got calcium inside. Calcium's going to do something. Step number 3. Calcium entry causes acetylcholine, a neurotransmitter, to be released by exocytosis. Okay, so in the picture, you see these little packages with green dots inside of them. The green dots are acetylcholine. Okay, you'll see it abbreviated ACH. And acetylcholine lives in those little packages and he stays there at the end of the axon terminal until he gets this signal. He's just chilling out, waiting to do his job. Okay? But now he's gotten the calcium signal. And that calcium signal says, time to storm the castle. So, these little vesicles fuse with the membrane and release acetylcholine into that synapse, the area between the axon terminal and the muscle fiber. Okay? So now we've got these little green dots of acetylcholine floating around. All right. So good? Okay. The little green dots are going to bind to receptors on the sarcolemma, on that muscle fiber. Pretty benign, right? They're binding to receptors. But wait, the receptors are ligand-gated channels. So, when the acetylcholine binds to the receptors, it's going to open a channel. Okay, and the channel is an ion channel. It's going to allow sodium and potassium to move through. Sodium is going to move a lot faster than the potassium. So we're going to get a lot of sodium coming into the cell and a little bit of potassium going out. Okay, what's that going to do to the inside of the muscle cell? It's going to make it more positive, right? Because we're putting in a whole lot of positives to the inside, we're only getting rid of a little bit of positive, so we're going to end up flipping that resting membrane potential. Now we have an action potential there on the muscle fiber itself. So we now have an inside positive and outside negative, which is, let's say it on yes. Okay. The acetylcholine binding to the receptors will cause a local depolarization. Depolarization is another way of saying we flipped it. It was negative inside, now it's positive inside. Okay? So we have a local depolarization, flip of charges. Okay? We call that change right there at the neuromuscular junction an end plate potential. So we're going to make an action potential from it, but right now it's an end plate potential. It's the potential that's right there at the neuromuscular junction. All right, so let's see if you guys can walk me through this and I have a video of it. Ready? Okay, what starts us all off? What's coming down the axon? A signal called action potential. It goes down to the axon terminus, And what does it do to the charge across the membrane? Flips it or depolarizes it. Okay? What channels are here that are voltage gated? Calcium. So once it recognizes that flip of charge, calcium channels open. Which direction does the calcium go? Into. What does the calcium do now? Causes acetylcholine to be released. It goes into the little synaptic cleft, and then it binds to receptors, acetylcholine receptors, which are also ligand-gated channels, which allow what to move? Sodium and potassium. Which direction does the sodium move? Into the cell. Potassium moves out. Okay, really quickly, we'll watch this video. I'll erase that once it starts.
Pulses, also known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles.
These videos are in mastering, and I'll also make sure they're up on Brightspace for you.
An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber. The events at the neuromuscular junction occur in 7 coordinated steps. Step 1.
Step one is really made of 7 steps.
Travels the length of the axon of a motor neuron to an axon terminal. Step 2. Voltage-gated calcium channels open and calcium ions diffuse into the terminal. Step 3. Calcium entry causes synaptic vesicles to release acetylcholine via exocytosis. Step 4. Acetylcholine diffuses across the synaptic cleft and binds to acetylcholine receptors, which contain ligand-gated cation channels. Step 5. These ligand-gated cation channels open. Step 6. Sodium ions, shown here in red, enter the muscle fiber, and potassium ions, shown here in blue, exit the muscle fiber. The greater inward flux of sodium ions relative to the outward flux of potassium ions causes the membrane potential to become less negative. Step 7.
All right, step 7 is turning the process off, which we'll get to later. So, guys, study for your test on Wednesday. I will see you Thursday. I'll see you Wednesday for your test. But Thursday, we're going to have a quiz. All right? See you guys later.